Let me introduce Rob McMullen. He's going to talk about data compression on the 6502.
All right, thank you. So I put an asterisk on my slide because I want to emphasize that this is not data compression on the 6502. We're not compressing data on the 6502. We're going to do decompression on the 6502 and compress it using modern hardware. But first, just to kind of gauge the level of where we all might be, I just wanted to know, have you heard the good news? So Kevin, could you lock the door? I'm going to start get the pamphlets going. I'm going to introduce one term of art, and then we're not going to talk about it again. So entropy, it has a special meaning in data compression. In physics, thermodynamics, it means the randomness of the usable heat that is available. When there's no entropy, it means everything's at the same heat. Like the heat death of the universe means that there's no way to get usable heat out of anything. Data entropy is just the amount of bits it takes to store whatever kind of data you're trying to compress. So a constant stream of ones has no entropy. It takes no data to store it. If you alternate 1, 0, 1, 0, it means it takes 1 bit of data to store that. If you have a set of just regular binary data, 0 to 255, it takes 8 bits. That's all entropy means. The interesting thing about entropy is it's not a perfect measure of how well you can compress something because the order matters, and I'll have a demo of that later. Mark Pelzarski, pardon me, talked about Applesoft Basic, and this is one of the first uses of compression that I ever had, but I didn't realize it was compressed. I didn't think the Apple II, when I was using it, had much data compression at all. Tokenization is really one of the simplest forms of compression. So Applesoft Basic is defined as a binary file. It's got a header, and then it's got a bunch of ways to compress the raw text down into a smaller format. So I will show you a little example. So this is a very, very simple Applesoft program. So let me go to my first demo here. Get rid of some of this stuff. This is Omnivore. It's a program I've displayed before. It's kind of my hacking program. So this is that same Applesoft converted into binary format. So these first two, so it's 27 hex bytes long, and these next 2 bytes are I forget what now. Gotta go back a slide. Oh yeah, it's the address in memory of the next 2 lines. That Applesoft assumes that the basic program starts at 801 hex. Do it again. So it says the next byte is at 80F. Then this is the line number 10. And then this starts with the tokenization. Applesoft tokens start with the high bit set. If it has the high bit set, it's a token. If it has a low bit set, which you can see over here, it's just plain old ASCII text. And a 0 ends the line. And then you come to the next line. And it says the address of the following line is going to be 81F hex, and that's line 20, and then etc. So back to the show. Another sort of useful encoding in 8-bit terms is run-length encoding, and there's a whole bunch of different, and a lot of people roll their own run-length encoding methods, and there's a bunch of ways to do it. But basically, anytime you see a repeat in a string of data, you replace it with some sort of delimiter and then the number of times that it's going to happen. So if we try a simple example, this first example won't compress very well because there's not a lot of repeating stuff. There's only repeating stuff here near the end. But so if you just use a simple example where we take assume the input's only alpha, and then we use numbers to indicate a repeat. So you have this big string of stuff that's not compressible, and then finally you get to 1. There. If you have data that's better suited for run-length encoding, and you have a bunch of strings of stuff, then you can see there's there's a definite savings in that. But this is still it's kind of a basic technique. It's useful in some instances, but you'll find with compression that you have to pick your algorithm carefully. This is a variable length coding. Huffman coding is one of the first. It was it's not Felicity Huffman. It's David Huffman, who's the guy who came up with this. He proved that it was statistically the most efficient way to encode using a variable length binary encoding. So basically, the idea here is you take a sorted list of all your inputs. The most frequently used stuff takes the smallest length bit stream, and the largest one takes the fewest bits. So this is not terribly useful for the 6502. I just want to go over it just because I finally understand it, and I thought maybe I could help other people understand it. It took me forever. So yeah, it's not useful for 6502 really. You can do it, but it's just not super fast. So I lost my mouse cursor. I don't know where oh, there it is. Okay, great. So if you take this string, it's got, and you sort it, it's got lots of A's, some C's, and then the fewest number of D's. So as a naive approach, thinking, okay, let's try a variable length encoder. Say, okay, let's try, give the A that B. And so then we try to encode. So we see an A, we get a 0, we get a B, a 1, da, da, da. So you get this bit stream, which it's great, it's very compressed. But then how do you decode it? The problem being is that this 0 could either be an A or the start of the C token. So there's multiple ways to decode it. What Huffman encoding does is it takes you start with the lowest, the fewest occurrences, and you get these, you start with 2. We're going to make a binary tree that we're going to be able to march down and find the encoding. So the lowest ones are the D and the B. So we make a little tree out of that, and then we combine the D and the B into a single node and stuff it back into the list, in a sorted list. So now our list looks like D and B, which still have a lower count than either C or A. So now, if we start with this, what's the lowest? So we have D, B, and C are now the lowest. So we take this tree, and now look at this top tree here. And then the D and B tree is existing here. Now we take the probability of DB plus C, which turns out there's 19 of those, and there's only 16 A's, insert it back in the sorted list again. And then we do it again. We see, okay, what's the convention here I was using is the lowest one with the fewest numbers was on the left of the tree, and one with the largest was on the right of the tree. So we get this tree. Well, what does that do? Well, so now it gives us the ability to come up with unique tokens for each one, and this time there won't be any that have a prefix that is a different token. Oops, back. So A being the fewest, and the way we generate this is actually we start here at the list and we just march down. So on the left side we have A, so that gets a 0. On the other side we come down to this group of tokens, but we still don't have a terminator yet, so we go down again. On the 0 side we still don't have a terminator, and finally we get to D, so that's where we get the 111 for that. Do that for the others, and we have this unique ordering. And now when we parse this thing, or actually when we encode it, we come up with a bit stream. We come up with a bit stream that will be decompressible uniquely. And the way we do that is when we first start coding, we can see a 0, and does that start anything? Well, it starts with A. The next bit we see is a 1, and it's indeterminate, so we have to take another bit. And now 1, 0, there's no 2-bit code that has a 1 and a 0, so we have to keep going. And now finally we have one that matches uniquely, and then we can output in the B and keep going down. And this is it's the basis for a lot of common encoders. A lot of things we use other encodings and then use Huffman encoding to sort of pack the dictionary tables that they use. So this one again, this is a different style of encoding because it's called arithmetic coding, which was under patents for a long time, and so it wasn't used a lot. And even now, it's not used for 6502 stuff because it takes floating point. But also, it was something I finally figured out, and so I thought I would just mention something about it. So you can actually get a coding out of a single floating point number by, again, you sort of group things by order of probability, and you encode it letter by letter, or token by token. So if you have this probability where you have 40% A's, 30% B's, 20% C's, and 10% D's, you look at the first token, which is an A. So you say, okay, well, that's the first 40%. The next token is a C. So you take that whole big ratio and squash it down to just in that 40%, but it's still the same ratio. So we're now looking at this area here. For the third token, you can take that same ratio, but then squish it down again inside just this little C ratio here. And so what you can do then is you can keep going, just if you can imagine like zooming infinitely into this thing, you have this lower and upper bound of a range, and as long as you pick a number between that lower and upper bound of that final one down way at the bottom, you can decode that by just figuring out that the floating point number is between these ranges. It's like, yeah, super not appropriate for the 6502 because many reasons. But it's the basis of several encodings, like JPEG, I think, has a version of this. But it's like, to me, it was mind-blowing that a floating point number could encode something. This is now the basis of a lot of general-purpose coding algorithms. This is Applesoft encoding. It's like, most common encoders you think of, like zip or gzip, LZMA, all those things use versions of these LZ encoders. What it does is that you have your data as you process it, and you keep a buffer of stuff you've already looked at. And as you go through marching down the next areas of your data, you look and see if it's matched anything previously. And if it has, you point back to that rather than encoding literals. So we'll take a look at just an example here. If this is your phrase, at an Atari Star Ward, have to get Atari in there somewhere. So when you first start processing, you don't have anything in your buffer. So the output would be the first character, literal A. And then you move your pointer to the next thing, and you look, and so there's nothing that matches in your window, your sliding window, which is the stuff you've already seen. So you output another one. And when we encounter this third character, we've already seen an A, but it's only one. We don't have a long match, and so it's depending on your coding system, whether you encode a literal version or a pointer back to that first character is dependent. It's coding dependent. So again, we don't have another one. Finally, we have here the next one. We have an ATA in the current string, but we've seen ATA before. So then in your output, you say, okay, well, I've seen that. I'll point back to position 0 and 3 character, so the 0, 1, and 2 you've seen before. And so instead of storing a copy of that, you store the pointer back to it. I mean, this is obviously a trivial example, and the overhead, this would not compress probably to smaller than the existing thing. But if you can imagine, long strings, you can see how this could provide compression. And you continue marching down, and then as the window fills up down here, you see it starts chopping characters off the front and adding characters on the back. And so that's how you can do this kind of coding in like a finite amount of memory. There's a bunch of trade-offs you can make as to how big your sliding window is and how much memory you have. But that really is the basics of LZ encoding, which is not as scary as I thought it was. LZ4 is an algorithm that is, finally, we're now getting to stuff that's particularly appropriate to the 6502 because it's integer-based. There's no bit stuff in there. It's all really just integers. It's broken up into 3 parts. There's a token, which kind of says what's coming up. Then it can encode 2 different ways. It can encode things that it's not seen before as literals, and then stuff that it has seen in the past and with a variable width and distance away. So how it works is it has a single byte. And what makes this work for the 6502 is it's small and there's no bit shifting. Well, it's not technically, there's a little bit of bit shifting, but they don't use bit values in the output data. It splits this first byte into a literal count and a back referencing count, which is the stuff that it's seen before. And then in order to get around this 15 bytes worth of data, it has this auxiliary count variables. So if you need more than 15 bytes, you add these auxiliary counts, and so you can store arbitrary length bits of data in this algorithm. And so I'm going to get into some more examples now of stuff that we can do, so just demo time. So first I'm going to do a little bit of look at tokenization. So this is Omnivore again. Oops. Just gonna add a hex viewer. Okay. So this is a Jumpman level. This is Kevin and I have been working on this for the Atari. So this screen uncompressed would be about 4K. Jumpman encodes this as a series of tokens right here in the level definition. So just over 256 bytes. So if I add stuff, I get the toolbar back. If I add stuff, you can see the data here changing, and Jumpman is able to draw this whole 4K screen in just 256 bytes by using these little tokens. So this is an indicator, and then it got to have an offset and a length, and then another. And so tokenization is a very useful feature because you always know more about your data than a general purpose compression algorithm. So if I ran this screen through even LZ4, it wouldn't get it that close. So tokenization is always an option. Let's see, what am I doing next? Oh yeah. All right, so this is an Apple II HighRes screen. And we all know how fun the HighRes screen is for ordering. So this is, so if I start selecting memory, contiguous memory, I've selected the first line, then I move down 64 rows, and I select the second line, then third line, then it goes back to the top, but 8 rows down from the top. So that's, if you look at it the other way, if you select a line here, it's selecting data all over the place. So how does that change with the compression? So let's select this. First we'll select the HighRes screen, and notice that it's left out the screen holes. We'll compress it with LZ4 here. Get rid of the disassembly. So we've got, almost 3 pages worth of data compressed. If we go back over in the hex, and if I try to select all of it, I'll get the screen holes, which won't be a fair comparison. So for some reason, it's broken if I try to select in one view and copy in another view. So I had to make a special command. Select HighRes without screen holes. But so now I'm going to copy using this viewer and generate a LZ4 compressed file. There's assembly. And so we've almost added an entire page. So even though it's the same data, the order that it was presented in makes a huge difference. So that is another thing to think about when you're trying to compress data. Okay. Oh, I just wanted to show, since everybody has an emulator nowadays, this is my emulator. So let me stop that. Anyway, so this is, so I'm running Jumpman around here. Oh, I died. Well, let's stop it before I died. And then go back again. Has everybody seen this before? The difference here is now I'm saving all these checkpoints in this list so you can compare. And eventually they'll be able to like tag all these with text stuff so it's easier to remember what's going on. But you can look at different frames. Say if you had a bug in something, you can start it again, from some point and try to regenerate the bug, and then you can compare, say, a good version or a bad version. Say if you had a Heisenberg or something that you were trying to figure out, be able to compare all of memory and show the differences in the hex. All right, and finally, let's look at some LZ4. This is Peter Ferry's LZ4 algorithm. It ran in 31 frames. So it decompressed. I think it's about a K and a half in 31 frames to a whole HighRes screen. And we're gonna pretend for a minute that Peter Ferry's not sitting over in the corner there, and we could ask him how that's done. I'm going to go through and kind of just step through and show you how you might reverse engineer something using this debugger. So first I'm doing just setting the HighRes screen, and then there's some variables to set up, and there is this output variable is what is used to write to the HighRes screen, or what the output of the decompressor. So as you go, this is the start right here of his algorithm. Actually, let me show you his algorithm just to, assuming you didn't have any source code, but this is what it is. Token. And right here is the shift for the back reference versus the literal token. And then we can see that here. So how you might go about reverse engineering this would then you'd start marching through here. And so this emulator, I can do both Atari and Apple in this emulator, and so the Atari is based on frames, and so I just decided, okay, well, Apple's based on frames as well. So there's each frame in the Apple is 17,030 cycles, I think. 65 cycles per line, and so that's what these numbers are here over here. But you can start going down, and this is a memory access viewer, so you can see I've just written a few bytes to the first couple bytes of the hex page, or the HighRes page. Although it turns out they're zero, so you can't really see them on the monitor. But I think finally one shows up. So I'm debugging here. This is not an active debugging session. I've saved every machine instruction between frames, and I'm generating regenerating the sort of the history on the fly. Eventually, I'll be able to start from whatever point you want, but right now this is all static after the fact. But if I go to the next frame. And there's still issues with this because sometimes it's confusing reads and writes on this intra frame stepping. But you can go backwards and so it's probably too much to go through an actual reverse engineering session here, but that it is available, or will be if I ever get this out of an alpha stage. So any questions about compression or this emulator or anything? Yes, yeah.
A real-time decompression of
That's what this was, I think. Let me reboot it. Like that. Sorry, it went fast. I should have. So we can reboot again. So this is LZ4. It was, let me see, where do I have it? Let me get the hex going here. Oops. Yeah, of course. It was, let me see.
What did you say
It's running at, yeah, it's the same frame rate, yeah. It was 31 frames, so half a second. So 31 NTSC frames anyway. Yeah. Yeah. Let's see, where's the... Sorry. Shoot. I don't remember. Oh, there it is. All right, so it's 2K. So this, not the title that LZ4. So 2K expands into 8K in 31 frames. If a straight copy would be about, well, 8K to 8K would be 4 frames, 5 frames, something like that. Anything else? Well, thank Peter Ferry for LZ4 code. It seems to be used quite a bit. I've seen it on Atari Age all over the place. Sometimes credited, sometimes not, unfortunately. But that's open source, I guess. But thanks, Peter. All right.